Morning. Good afternoon, actually. So, yeah, we're gonna continue talking about the greedy algorithms, right? So last time we have finished the activity selection problem, and today we will look at the next two types of problems: Huffman codes and knapsack problem. Okay. So these are very typical problems that can be solved using a greedy algorithms. Well, in fact, when the solutions for these problems are first invented, I don't think people will realize that, okay, this is a greedy solution, but a greedy algorithm is just a way to summarize the common places of the algorithms adopted in these problems. Okay, so let's look at the Huffman codes first. All right, and so in practice, it's a very commonly used algorithm for data compression. Okay, so the codes here actually refers to the process of encoding data, like encoding string data, or basically what kind of data, any kind of data into a compact binary format. Okay, so in this example that we use here, the data is actually a sequence of characters, and our task is to basically represent each character using a binary code. Okay, so this is also a very common scenario in natural language processing, that when we want to input a bulk of text, okay, into the machine learning models, like we basically need to first represent this text like as a sequence of characters. Okay, and the most efficient way to store and retrieve this sequence of characters is that we want to encode them into a binary format that is efficient, okay, memory-wise, memory usage-wise. Okay, so the basic principle is that we need to use the frequencies, use the frequency information. Basically, it's a table of character frequency, and then we use that to represent each character as a binary string. Okay, so hopefully to optimize the way of encoding, so that as few memory space is used as possible. Okay, so for example, in this table, like we use a rather small vocabulary, and we assume that there's only 6 unique letters or characters in our data. Okay, we only have from A to F. Okay, and also the second row, it shows the among our data sets, it counts how many times the character A has appeared. For example, in this case, the letter K, the A has appeared for 45,000 times, and less for B, which is 13,000 times, and so on. Okay. So next, in the next 2 rows, here we show 2 ways to encode the letters in a binary string. Okay, the first is called a fixed length. So as the name indicates, for each character, we will encode them with a code that has the same length, with fixed length, and it's 3 binary digits, right? With 3 digits. So for A, we use 000, and for B, we use 001. So it's just like a binary number, right? We increment this encoding by 1 for each character. Okay, so this is so-called fixed length code. And on the other hand, the second row, the variable length code is actually our focus today. Okay, so we will use a different length for different characters. Okay, and you can see that the letter A has just 1 digit. Okay, it's just 1 bit. Okay, so this 1 bit, either 0 or 1, we use 0 to indicate this is A. And for B, we will have 1, 0, 1. Right? And for C, we have 1, 0, 0. And for the E and F, we use 4 digits. Okay, you see the difference here? We use different lengths for characters with different frequencies. Okay, so maybe the intuition already tells us that, okay, this might be a better way because the character A is the most frequent letter in our data. So it makes sense that we use less memory space. We use less code to encode the most frequent one. Okay, so this is a very smart principle, and let's basically check out how we achieve this, how we implement this algorithm in an efficient and in a valid way. Okay, so let's if we simply count how many number of bits needed for different ways of encoding. Okay, so 1 bit is for just 1 digit here. So this 1 digit is 1 bit. Okay, so for the variable length, it's 45 times 1, right? Because A appears 45,000 times, so it'll be 45 times 1. And for B, it will be 3 times 13 because it appeared 13,000 times, and each time we need to use 3 bits, and so on. So for all the letters, we can use the summation of these products to calculate the total number of bits required using this encoding schema. All right, so the difference is there. Obviously, the variable length code is better, right? Because it uses less bits. Okay, because bits is the way to quantify the amount of information required, right? So this is the obvious, a very an advantage of this variable length encoding. Okay, so for using the variable length encoding, there's a technical issue we need to pay attention to, which is that these particular codes, variable length codes, needs to be a prefix code. Okay, so this prefix code is a property that makes sure no code is a prefix of some other code. Okay, so if one code is the prefix of the other code, then it causes ambiguity when we decode in the decoding stage. For instance, if we encounter the binary sequence like this, which is 001, 011, and 101, right? So how do we decode this sequence according to the table, right? We have 2 ways of decoding, right? So if it's the prefix code, then we can, when we first meet the first 0, right? The table will tell us, okay, this is a letter A. And then when we meet the second 0, it's another 0, right? Then the table will tell us it's A again, right? And when we meet a 1, then the next 3 letters is, oops, is 101, right? Right. So 101 would be. So if we decode this sequence, use the prefix code encoding schema, it will be AABE, right? There's no ambiguity at all. But it will be not the case if we use the non-prefix code, which is that, okay, you see the the code for A is 0, right? But the code 0 itself is the prefix for C, right? It's also the prefix for the D here. 0 has appeared as the first letter in these 3 encodings. So this causes trouble for us. So like for the same sequence, if we look at the first digits, right? So there's two different ways to interpret, right? It could be either an A, right? Or it could be the 2 consecutive zeros, which corresponds to the code for C. So this is definitely what we don't want, right? We want to a unambiguous decoding and encoding. Okay. All right. So basically, our task is to get and then design an algorithm to efficiently encode each letter according to their frequency, so that the codes are variable lengths, and more importantly, they are prefix codes. Okay. Anyway, so the data structure we're going to use is a binary tree. Okay, so a binary tree can provide actually a very convenient representations for the prefix codes. Okay, and in the tree we will have leaf nodes and non-leaf nodes. So the leaves in this case, which are the most bottom nodes that do not have children nodes, those leaf nodes are characters. Okay, and the code for a character is the path from the root to that character. Okay, so for example, this is a binary tree that is already encoded. It's already built, okay, or drawn. So this tree is complete. So if we look at the binary, if you look at the leaf nodes, they are all in these boxes, okay, or in these rectangles. Okay, so we also attached the frequencies to that letter, right? Just for information, just for showcase how the A has the shortest path, right? So if you look at the path for A from the root, so this top node is the root node. If we go through the A to the root node, we will have just 1 digit, which is 0. Okay, and this 0 is exactly the prefix code for the letter A. And for C, right, if we look at C, it's right here. If we go, and we need to go from the roots to the C to find its path. And along this path, we will have 1, 0, and 0, right, which is exactly the code for C. And similarly for B, right, it's 1, 0, 1, right? And for all the other characters. Okay, so this is the way we're going to use to represent the encode, for represent the code, the prefix codes. Okay, so the 0 and 1s means that this is the if it's a 0, then we go to the left child, and if it's 1, we go to the right child, and this is very clearly defined here. Okay, all right. So the binary tree should be a full tree, which means every node in the middle, which means they are not leaf, every non-leaf node should have 2 children. Okay, there shouldn't be a left, and there shouldn't be an empty branch. Okay, so the tree corresponding to the fixed length code is not necessarily full. So you will see that if we compare it with the variable length, the code, which is here, right? So this is the prefix code that we looked at before, but this is the fixed code, which is not the most efficient way of encoding, right? So if it's a fixed code, then you will see that the node for this one, for this 14 node, there's no left, no right branch. Okay, so this is something that you can immediately tell from the shape of the tree that you have grown. Okay, so what we essentially want is something like this, a complete tree that each internal node have both children. Okay, all right, some further properties for a full binary tree. And let's use this capital C to indicate the alphabets or the vocabulary. Like C basically is a set of all distinct characters used. That's a good question. I see a question that's is this, I'm gonna resend it. So it is a how ask-to codes work. I don't know. I need to look into that. Not sure though. My feeling is that it is not. Okay. So because at least the ask-to code for the letters should have they are just integers, integer numbers, right? Right. They are not binary encodings. Yeah, I haven't thought about that. Yeah, but it's interesting to look into. So back to the binary tree here. So we use the capital C to indicate the complete set of all characters. Okay. Then the tree, we use the size. So this size of the set actually is the number of leaf nodes or leaves in the tree. Okay. So one leaf is for each letter. Okay. And there are C-1, the size of C-1 internal nodes. Okay. So that is something you can examine quickly from this the example trees. We have 1, 2, 3, 4, 5, 6 leaf nodes for 6 letters, and the internal nodes are those circles, right? We have 1, 2, 3, 4, 5 internal nodes. Okay. So yeah. So now the question is that how we can actually construct a optimal prefix code. Okay. We actually already know the intuition, right? Because we want to for those frequencies that have lower for those letters that have lower frequencies, they are like rare letters that don't appear a lot in our data. Then it's okay that they have longer paths from the root node, right? Which means they have longer codes. Yeah, because they are rarely used, so it's okay we assign some longer codes. That's a rational choice, right? And for those that are on the other, obviously, like for the more frequent letters, of course we want to save space, right? Because they're used so often, so it makes sense to just use 1 or 2 or even shorter. Just use as few as codes as possible for those frequent letters. Okay, so it's basically following this intuition, we can like construct the binary tree using a bottom-up manner. Okay, like we can start from the least frequent letters and then we put them into the bottom of the tree, and then we gradually grow this tree from a bottom-up style, using a bottom-up style. Okay, so we should select those letters that are least frequent in the vocabulary. Okay, in this case, it's the letter F and E, right? One has 5 and one has 9 frequencies. Okay, so again, let's get some preparation by looking at how trees are constructed. Basically, we need to have a node, right? The node here in the middle, it's the so-called parent node. It's at upper level and it has 2 branches, one pointing to the left child and the other pointing to the right child, right? So we in a tree node, we can using this pseudocode convention, we can use the z dot left to indicate that it's the left child for the parent node z, okay, and the z dot right points to the right child of the parents. Okay, so we can create a tree basically by assigning some other letters or other nodes to the left pointer of a parent node, right? So like we can construct the parent node z by assigning the node x to the left pointer of Z, right? Use this assignment statements, okay? And we let Y, the node, to assign to the right pointer of the parent node. All right. So, and we can also easily check whether a node is a leaf node or not. So we basically look at whether the left child and the right child pointers, they are nulls. Okay, if they are all nulls, then it's a leaf node. Okay, and in our particular example here, in order to visualize the whole process, we will also attach the frequencies for a letter to each node. Okay, so we can access the frequency for each node quite easily. All right, we have everything ready now, and let's look at the code for Huffman coding. Huffman codes algorithm. So it's takes inputs the vocabulary or the alphabet C, which is a set of n characters. Okay, indicates the n unique characters that have appeared in our data. Okay, and for each character, we will have a frequency attribute by c.freq. Okay, so the first line is to count the size of the C, like how many letters we have, and the second is to use a minimal priority queue. Okay, so this minimal priority queue, it's like a queue data structure that's in which all the elements is assigned with a score. Okay, and this score indicates a priority of the queue, which determines whether when that element is gonna be dequeued. So the element that has the highest priority will be the first one being dequeued. So that is basically how a priority queue means. Okay, so what about this minimal priority means? So this minimal priority means that the elements that has the minimum score in that queue will have the highest priority. Okay, so it sounds like two concepts. It's the priority, it's the score, right? So so we can basically say that the smallest elements in that queue will get dequeued first. Okay, no, regardless of the order of when that queue entered the element, when that element entered the queue. Okay, all right. So this data structure is something we're gonna use for store all the letters. So we're gonna initialize the minimal priority queue with all the distinct letters we have. Okay. Then we will have a for loop. Okay. So that's the minimum priority queues. Okay. So the queues will support the operation called extract minimal queue. Okay, so this extract minimal queue is something is a process or procedure that's gonna let the smallest element in the queue pops out. Okay, so this is a key operation that we will use. Okay, and also there's another operation that is for the minimal priority queue, which is insert. Okay, so this insert is just to insert some elements into the queue. Okay, so let's see the body of the for loop. Okay, and it's quite straightforward code. Line 4 is to allocate some new node. Okay, so this new node is something we created at the beginning of each step. Okay, and how do we create that Z? Is that we need to first extract a minimal elements from the queue. So the X is the one that we extracted from the queue. Okay, so at the beginning, the queue is full of letters, right? So we can extract one element out. So what we do with X is that we assign X to be the left child of Z. So it basically looks like this. We will put a Z here. Z is an empty node, okay, at the beginning. And then we will assign the X to the left of Z. And then we extract a second element from the queue. Okay, so other than X, because X is already popped out, then Y will be the next smallest element in the minimal priority queue. So Y will be extracted, and it will then be the right node of the Z. Okay, so the line 9 is that we compute the summation of the X node and the Y node, and we put the summation to the frequency attributes of the Z node. The Z is the new node being that has been constructed. Okay, and we need to put the Z, the new node Z, back to the queue. Okay, but it's not put X and Y back. X and Y are already popped out, but we'll put the Z back. So Z is a new objects in the memory space. It's a new node. Okay, so that means in each iteration of the for loop, like we extracted 2 elements out and we insert 1 element back. So the size of the queue actually decreases by 1. Okay, so this is a decremental algorithm. So whenever each iteration will decrease the size by 1. So eventually we're going to have just 1 elements in that minimum priority queue, right? So we let this for loop iterate from 1 to n minus 1, right? So when this for loop ends, there's only 1 element left in the minimum priority queue. So that's why eventually we're gonna extract that last element from the queue and return it. Okay, so the returned node is the root node that points to all the elements that contain that contains a complete Huffman tree. Okay, all right, so let's use an example to showcase this process. All right, let's initialize Q. Right, so the Q is actually everything we have from the alphabets, right? So I put those letters in order such that you can see the first letter that has the least frequency score is the leftmost, and all the letters are ordered by the frequencies. So the leftmost one has the highest priority. It will be the one first being extracted. Okay, so extract the minimum priority queue will pops out the node for F, right? Letter F. And according to the algorithm, we need to extract 2 nodes, and the next one will be the letter E, right? Because it has 9 as the frequency. So now we're gonna make a new node Z, right? And the frequency and the F will be the left child, and the E will be the right child. Okay, so the frequency attributes for Z would be 5 plus 9, which is 14. Okay, now we have this new structure constructed. So we will have a Z, new node Z, and then this Z will be inserted back, right? The new node Z will be back to the queue. Okay, and by inserting it to the queue, which means it will appear at the proper at the correct position, because it's a minimal priority queue. That's it has the node being inserted has the frequency 14, and which means it will appear at this position because it has lower priority than the B, and it has higher priority than the letter D, right? Because the frequency is in middle. Okay, so that is how the basically how the minimal priority queue maintain the sequences for all the nodes in it, right? And we will let this procedure continues. Okay, and then we will further in this second iteration, we will extract the letter C and B, right? And after they are extracted, they will construct a new node, and this new node will be inserted, and this C and B, the frequencies add up together to 25. So this new node will be inserted to this position because it's higher than 16 and lower than 45, right? The next iteration gonna be a little bit different because the extracted node would be the node that we created at the in the first iteration, right? It is the node Z, right? So this new node will be extracted altogether as a complete unit, okay, as a whole unit, okay? And the next one would be the letter D. All right, so now let's merge them into a new node. We just follow the same principle, right? In this new node, the left child would be these parts, which is exactly node that we extracted, okay? Because the frequency is 14, which is lower than the frequency 16 here, right? So the new node created is actually this root node that has a summation between 14 and 16, which is 30, right? So this is how we construct a node with two nodes, right? The first node is itself a composite of other nodes. Okay, so yeah, we have a very big node now, and that big node with 30 as the roots node elements will be inserted back as well. Okay, so this 30 will be inserted back, and now it's in the correct position right after the node 25. Okay, all right, so we will continue this until our minimum priority queue is empty, right? So the next one being extracted, the next two being extracted will be these two nodes, and we're going to compare their root values, right? And we compare an even higher, even larger node, which has 55 as the root node, okay? And this node is again inserted back, okay? Now we have the last two elements, so we will extract them all and construct a final node, which has 100 as the roots node value. And this one will be inserted back into the minimum priority queue. And at this point, our for loop is also done, right? Our for loop is done, and this one will be extracted, will be returned, okay? And this is exactly what we need in order to construct a Huffman code tree out of the frequency table. Okay, we will need to utilize the data structure called the minimal priority queue. Okay, and if we examine all the passes from the leaf nodes to the root node, we will find that it is actually correct. It produces an optimal prefix code. Okay. So actually the correctness, how do we prove the correctness of Huffman code algorithm is pretty complex, and it's not required, but if you are interested, you can read the proof yourself from the textbook. Okay. So let's look at this Huffman code algorithm, and it belongs to, we can categorize it as a greedy algorithm because it's making greedy choices in each step, right? So the core concepts that is of our interests about some encoding is that we want to minimize the total cost, right? To encode the file, we want to use as few bits as possible. That is our goal, right? So the total cost in this particular example would be the summation of a bunch of products, and the product is between the frequency and the depth of a node, right? You see, when we want to compute the total cost, we need to look at, okay, A is here, it has frequency as 45,000. We need to use that to times the depth of A, which is also the length of the optimal of the encode, right, of the Huffman code. So it'll be the depth of A. So these total cost would be our goal to minimize, right? So if we represent it with a cost function, it will be like this, right? It will be like we want to enumerate over all possible characters in the data, and then we use its frequency times the depth of that letter in the in the tree. Okay, so when we construct a tree, use this bottom-up manner. We will first the first chosen nodes, right? The early picked nodes will have a larger depth. Okay, so therefore it makes sense that the greedy choice is to choose the two nodes that are lowest frequencies, that are the lowest, that has the least frequencies, in order to minimize the cost of the current step. Okay, so you see the key is that when we choose the lowest frequencies, when we choose the two nodes of the lowest frequencies, we are not sure whether this gonna minimize the goal, the global goal. Whether we are gonna have a final minimized cost, that is something we are not sure. We just know that by choosing the two minimum frequency nodes will minimize the cost of the current step. Okay, that makes the current choices make sense, right? We want to choose those elements that has fewer frequencies because they are at the bottom, near the bottom of the tree. Okay, but we don't know whether this is going to be a globally optimal choice. So that's where the greedy choice property is from. All right. So let's look at the running time of this Huffman code algorithm. Structure-wise, it's a pretty simple algorithm because it has just one for loop, and the iteration is determined, right? It's like n-1 iterations. Okay, so the thing is that we have some calls of these extract minimal elements of the queue. Okay, so it depends on the data structure, the minimal priority queue data structure, right? We need to look at how fast the data structure is in supporting the pop-outs and inserting procedures, basic operations, right? So the minimum priority queue is actually, we actually have mentioned that a bit when we introduced the heap sort, when we use the max heap, right? So I remember there's a slide showing that saying that the minimal heap can be used to implement the minimal priority queue. Okay, so a little bit review here. A heap is like a tree structure, right? So the max heap that we use for a heap sort is that the parent node always have bigger values than its children node. So the minimal heap is the opposite, which is that the top elements or the parent node has smaller values than the children nodes. Okay, that's for the minimal heap. Okay, so if we use the minimal heap to implement this minimal priority queue, then we're going to have a logarithm of n running time for these heap operations, for these extract min and insert elements operations. Okay, so it's just a little bit similar to the max heapify procedure. It's like whenever we change the positions of the elements in it, like we extract the one element out, we need to like use max heapify or minimal heapify in order to maintain the max heap or minimal heap, the min heap properties. Okay, so altogether we have logarithm of n basic operations within the body of a for loop. So altogether, it's going to be big O of n times logarithm of n efficiency, running time efficiency. Okay. All right. So let's finally review the greedy algorithms a little bit. Okay, to look at the elements of the greedy algorithms so far. So by greedy choice, we mean that the globally optimal solution can be achieved by making locally optimal. Okay, so this locally optimal choice is the so-called greedy choices. Okay, so we make the choice that it looks best in the current problem, but we lack the information. There's no information telling us that these results, whether these results gonna be lead to the globally optimal ones. So we don't consider the results from all the sub-problems. Okay, and the greedy algorithms usually also represent some optimal substructure. Okay, also can reflect some optimal substructure, which is similar to the dynamic programming algorithm. That's the solution, the optimal solution to the original problem contains optimal solutions to the sub-problems. Okay, but the thing with difference with DP is that we actually do not need to solve all the sub-problems for a greedy algorithms problem, because this particular type of problems makes sure that making a greedy choice in one original problem is enough. We don't need to compare over comparing over the solutions from all the sub-problems. We just solve one resulting sub-problem using some simple heuristics. So that is the connection between greedy algorithms and the dynamic programming. All right, let's look at the last example for greedy algorithms. Okay, so it's actually pretty. So we will draw a connection. We'll draw a comparison with dynamic programming for this problem. Okay, so there's actually two types of knapsack problems. The first one is called 0 or 1. Okay, so it's also called discrete knapsack problem, and it's quite easy to understand actually. So it's like a thief. That's how the original problem is defined. It's like a thief robbing a store, and he finds that there are multiple items to take. Okay, say assuming we have n items. Okay, and he knows the value for each item as well, and the weight as well. Okay, so for example, the ice item has the value vi and has the weight wi. Okay, and assuming that all the v's and the w's are all integers. Okay, just for simplifying case. Okay, so he has a limited capacity in his knapsack. Okay, so he can carry at most w pounds. So at most the w pounds, and the goal is that to optimize the values. Okay, so he wants to take as many objects and many items that are as valuable as possible. Okay, so in this simple example here, if he has 3 items to choose from, right? The first one is worth $60, and it's very light, right? It's just 10 pounds in weight. And the second item has $100 value, but it's heavier. It has 20 pounds. The third one is the most valuable one, but it has it also the heaviest. It has 30, right? 30 pounds. So given a capacity that is like 50 pounds in total, right? He can carry 50 pounds at most. So what would be the best choice? So I think in this example, it would be easy to enumerate all possible combinations, right? So like if he takes item 1 and 2, it'll be like 60 plus 100, which is 160, right? If he takes 10 plus 30, if he takes the item 1 and item 3, right, it's still within the capacity, right? So it'll be 180. And of course, if you use the most of these knapsack, it'll be like 100 plus or 120, which is like 220, which optimizes his like revenue or his outcome, right? So that's a pretty obvious solution in this simple case, okay? But if we got a general solution, if we want to get a general solution out of some more items, and we want to solve that problem in an efficient way, then this problem is not that easy. Okay, so it has to be solved by a dynamic programming algorithm. Okay, and I'm not going to show the solutions for a complete solution here, but you can actually find it from the textbook in those pages. Okay, so well, this is just a dynamic programming problem, right? So if we like change the definition, change the algorithm, the problem a little bit, then we will have a very easy greedy algorithms solutions actually. And this is actually called a fractional knapsack problem. Okay, so the difference is that the thief can take actually fractions of items. Okay, it doesn't have to decide whether to take it or throw away one item. It's not like that. It's like he can have part of the object, part of the item. Excuse me, like he has a gold dust, right? He can use like pouring the dust into his knapsack as much as possible, like that, something like that. So it's called fractional knapsack. So in this case, it actually makes the problem quite straightforward to solve. Okay, it's a very easy greedy algorithm thinking. It's like we can simply pick the most valuable item by looking at the rate, by looking at the ratio of value versus weight, right? So if that ratio is the highest, then we say that this is the most valuable thing to pick, right? It's like the unit price, for each items, because we can take a proportion of it, like whatever proportion we would like. So that will make the whole solution quite different. Okay, so if you look at the unit price for these three items, so these numbers are the same from the previous slide. But if you think of the unit price, so for the first one, it actually has 60 over 10, which is 6, right? And the second one has a lower unit price, which is 100 over 20, which is 5. And actually the item 3 has the lowest unit price. Okay, so according to our strategy, our greedy strategy, we want to take those objects that has the highest unit price, right, as much as possible. So the solution would be like, we will fill out the knapsack with these most valuable items first, right? That'll take up 30 pounds. And what we're gonna do with the next is that there are 20 pounds space left, right? We're gonna take that 20 over 30 proportion or fraction out of this item 3. We only take 20 pounds out of this $120 item 3. Okay, so that will be 60 plus 100 plus $80. Okay, so that actually maximizes the solution, and it's even better compared with the previous 0 or 1 knapsack problem. Okay, so yeah. Anyway, I hope this example makes the showcase that the greedy algorithms sometimes the same problem can actually be converted into a totally different problem. and typically speaking, the connection between these two different types of problems it usually can be solved by the more complex one can be solved by dynamic programming, while on the other hand, if we think of it in a different angle and change the condition a little bit, then it becomes a problem that can actually be solved with a greedy solution, which is much easier to think about, to come up with a solution. All right, so that's so much for the greedy algorithms today. And actually, I don't have more slides today, so I will end the class a little bit earlier. And the algorithm, no, the assignments for the greedy algorithms, I will release it this evening, later this evening tonight. Okay, so it will be like several problems you can work on about the activity selection, about the Huffman codes, and some other types of problems that can be solved from a greedy selection, from a greedy choice perspective. Okay. Yes.
Professor?
Yes.
Regarding the current assignment, the one about dynamic programming, I recall earlier on you said it would be due this Friday, but the Canvas says it's due the 23rd, which is...
Yeah, I extended that.
Okay.
Yeah, extended so that I can give you more time on the problem. Yeah, I thought this Friday would be too tight. Yeah, so that's the question I see here. It's extended. Okay. All right, so I will end the class earlier, and everybody have a good rest of the day. Thank you.